Okay, so this just goes back and again, just shows once again the carbonyl system. Here I have it for a ketone, in which I can break to form two types of acyl ions through alpha cleavage. Okay, again, most books show it this way. Again, I'm pushing it, I'm sharing, it's better to show it this form. So again, on my exam, if I ask you for the molecular ion peak, I don't want to see this. I want to see specifically this one. Okay, why? Because again, it's easier for you guys to show me the arrow pushing that results to form these different species. If I break this bond homolytically here, I get R dot, plus I get a new acyl ion in which I push this guy here and this guy here to generate that. Again, here's the resonance form of this acyl ion where this carbon is positive, but again, since this carbon doesn't have an octet, this is the better resonance form in which the charge is on the oxygen. Again, this is something Dr. Schwann should have taught you when you were talking about Friedel-Crafts acylation. Okay? So if I break this bond, it leads to this acyl ion. On the other hand, if I break the carbon R dot bond, I generate a arm prime radical plus this new acyl ion. So with ketones, I can often see that it goes in both directions to form both acyl ions. Okay? So as I pointed out, the McLafferty of carbonyls is a system that has to basically, it's a paracyclic reaction or a considered reaction. I just switched it on you a little bit. So here is the radical cation in which the radical's on oxygen here. If I take this pi bond and form a new bond to new oxygen hydrogen bond here, and then if I break this gamma CH bond to form the alkene, and then I'm breaking the alpha beta bond to form a new enol system plus the alkene. Okay, so again, Y could be anything. So Y could be, again, aldehydes, ketones, amides, esters, whatever you call it. Okay, what I don't have here, and I won't ask this, but again, I just want you guys to conceptualize this. One of the things we just learned in these past few chapters, particularly in the carboxylic acid chapter, is that nitriles belong in this category. So if this was a nitrile here, all I would have here is a nitrogen with a radical. Nitriles can also do McLafferty's, but again, you still have the same requirement. You must have a hydrogen on the gamma carbon to the nitrogen carbon. Okay? So here's an example of that. Let's see if I can do it with you guys. So this was taken off my so this was taken off an exam I gave many years ago. Okay. So here's the example, and again, I'm going to give you guys some of these examples for additional problems. The question says the following is the mass spectrum for 2-octanol. Okay, so I give you the structure of 2-octanol. For the peaks label, please show their structure and indicate how they are formed mechanistically. Also indicate the name of the fragmentation for each peak. Okay. So obviously I'm asking in this problem for students to assign the peak at 128, 113, 58, and 43. Okay, so we'll have to do 4 of them. Okay. So basically what I would like you guys to do is start off with the molecule. So I redrew the molecule, but this time I just flipped it, where I put the carbonyl on the far right and the methyl group. Okay, so the first part is as you take this molecule, the first thing that we got to do is in order to start the mass spec experiment is to vaporize it, and then in the course of the vaporization, we pass it through an electron filament. That's again under high vacuum, and what that does is basically makes, I'm going to show it this way because I'm losing space here. So So I have 1, 2, 3, 4, 5 methylenes. I'm going to put 5 here. And I'm going to show my carbonyl. And I'm going to show the methyl. Okay? Now recognize in this molecule, this ketone, I have sigma bonds, I have pi bonds, but I have non-bonding electron pairs. In general, what I want you guys to do is show me that the radical cation is formed here. So this is my Me peak equal to, what is it, 128. Okay? So that's the first part. That would be some points you would get. Okay? Now that you have that, let's see if we can start playing with this and start doing some things to do this. So I'm going to start off with alpha cleavage. And if I redraw it, one, two, three, four, five. 1, 2, 3, 4, 5. I have this guy here, so I'm just showing my radical cation and the CH3 group. Okay.
That's it.
Up, please.
What?
Move the paper to the right. Yep, that's perfect. Thank you.
Okay. So in alpha cleavage, I'm going to break this bond here. So I'm going to break this bond homolytically. And so that means I'm going to take this electron. Oops, let me do it in red. I apologize, I don't have a green pen here. I'm going to break it that way. And I'm going to break this guy this way. And I'm going to take this electron here. And so what that would ultimately give me is an alpha cleavage. And I'll just write alpha cleavage again. And that gives me, let's see, CH3, CH2, CH2, 1, 2, 3, 4. 1, 2, 3, 4, 5. Plus a methyl. Let me draw it this way. Okay, so that's my methylacylamine. What's that? That's 12 plus 16 is 28, right? 28 plus 15 is 43. So that would be my 43. I would just ask you to circle it. Okay? So we got 2 of those down. Now, I obviously have another way that this could lose. You guys see this? You need me to go up a little bit?
That's perfect.
Okay. Someone asked me to put the document camera closer, so unfortunately it does limit my writing surface, but not a big deal. Okay, so here is my ion peak. And again, the other alpha cleavage would be to take this electron, push it here, and then break this bond homolytic. So if I do that, I'm going to shorthand it. There's 5 of these, 1, 2, 3, 4, 5, and I would form a acetylene that looks like this, plus methyl dot, and this would have an Me. So if this is 128, 128 minus 15, I'm getting old, is what, 113. And so again, all I ask you to do is to circle this. Okay? And again, this is an alpha cleavage. Okay? So I got 3 of them, I'm down to 4. Okay? So the next peak I need to do, God, my eyesight's terrible, is to show a peak at 58. I'm almost positive it would be the McLafferty. I'm just going to go ahead and do it just to demonstrate the McLafferty with you. Again, it's formally called the McLafferty rearrangement. Okay, so again, what I'm going to do is show this guy in this fashion, but I'm going to try to draw this guy in a 6-member type of system so I can push the arrows. Okay, so this is my alpha, this is my beta, this is my gamma, and my gamma must have a hydrogen. So I'm going to put a hydrogen out here, and then I have CH2, CH2, and is that right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and a methyl. I'll put the methyl this way. Okay? So now that I have that, this will undergo the McLafferty. And the McLafferty is nothing other than just basically taking this pi bond, I'm going to push it here. I'm going to take this gamma CH bond and form a new pi bond here. And then I'm going to take this guy, and this alpha beta bond breaks to form an eno. And so if you allow me to redraw this, you have CH3, CH2, CH2, and I have a new double bond here, which we don't see, but what we do see is the eno that's formed. Here. Okay, and so this is positive here. And this should be an E. So that's 14. 14 plus 12, what's that? 14 plus 12, I'm getting lazy. 26 plus 16. 42 plus 15 plus that hydrogen, 16. 58. So all I do is do that. Okay, so again, specifically here, this is what I'm asking you guys to basically apply on the exam. Okay, so I'll ask 1 or 2 questions and ask you guys to do some of this. In this example, notice that I didn't show that I didn't ask for systems where the stellium ion loses a molecule of carbon monoxide to make the, I could ask that. I didn't show any beta. But in general, I will tell you, I will definitely ask you to do an alpha cleavage and probably a McLafferty. Okay, so again, this is very similar. And again, what I'll do today after class is I'll post that problem set and